Okay, this is where we left off last time in Nice. It's a nice place to start from. So there's a command called nice, and it's used to run command with a particular CPU priority. You can give it more or less CPU than other processes. So nice essentially is called nice because it's how nice are you? Do you let the CPU do you let the operating system give the CPU to other people? Right. In other words, everybody gets a fair share of the CPU, but you can be nice and say, I relinquish my CPU, let other people have it. So let's talk about nice. On a theoretical basis, a niceness of -20 is the highest priority. In other words, if you had a niceness, you're not nice at all. You're a negative nice. You're mean. You take all the CPU. You want all the CPU at least. And 19 is the lowest priority. 19 is saying I'm super nice. That's as nice as you can get, 19. The default niceness for processes is inherited from its parent process and is usually, so when you create a process, it gets the same niceness. And it's usually 0. So you can basically assume that your process, if it is an average process, therefore its niceness is 0. It's not particularly nice and not particularly mean. The golden mean. Nice becomes useful when several processes are demanding more resources than the CPU can provide. In other words, if everybody wants the CPU and they're all getting it as much as they need, then there's no problem. But what if they want more CPU? Well, theoretically, everybody wants more CPU. In this state, a higher priority process will get a larger chunk of the CPU time than a lower priority process. In other words, either he'll get served more often this time slice, or his time slice will be just larger. Generally, only here's a key point. Generally, only the super user root may set the niceness to a lower value, which would be a higher priority. In other words, I can't just say, I'm mean, I'm -920. You can't do that yourself. You can make your niceness higher. You can say, oh, it's 0 now. I want to be more nice. You know, everybody is able to give up their rights, but nobody is able to get more than their rights. But let's say, for example, a user wanted to compress a large file, but he didn't want to slow down other processes, maybe his own processes. But he wants to get it going. He doesn't want to forget to do it. So he might run the following command, nice -n19. That means run the following command with a niceness of 19. That would be the most nice he could make it. But it's only going to be for this following command. tar, and then the file that he wants to compile. You know, these are some flags for tar. File he wants to make, and the large file. So in other words, he's going to compress the file on his system using the tar function, but he's going to run it in a way that it won't take more CPU. You know, it'll take as little CPU as possible. So therefore, it'll take longer, but he doesn't mind. Now I have the math of nice. It's a funny sentence. The mice of math. The mice of meth. The meth of mice. Anyway, the exact mathematical effect of setting a particular niceness value for a process depends on the details of how the schedule is designed on that implementation of Unix. So the exact mathematics we can't exactly say. A particular operating system scheduler will also have various heuristics built into it. For example, to favor processes that are mostly I/O bound over processes that are mostly CPU bound. You might give more CPU to an I/O bound process because the I/O bound process very rarely wants CPU. So whenever he wants it, I'll give it to him, and then he'll give it back. A simple example: when two otherwise identical CPU bound processes are running. So what does it mean, CPU bound processes? We're saying these processes are only interested in CPU. They just want CPU, CPU, CPU all the time. They're not interested in relinquishing. That's just to make things clear. And they're running simultaneously on a single CPU Linux system. Each one's share of the CPU time will be proportional to 20 minus P, where P is the process's priority. Remember, 20 is beyond the niceness that you're allowed to be. So thus a process run with a plus 15 niceness. What does that mean? He's saying I'm extra nice. He'll receive 25% of the CPU time allotted to a normal process with a 0. How do I get that? Because I do this 20 minus p. 20 minus p minus 15, that's my niceness, divided by 20 minus p minus 20 minus p, where the p is 0. In other words, he's a normal process. His priority is 0. So you get is 5 divided by 20, or a quarter. So that quarter means that the process will receive a quarter of the CPU time allowed to the other guy. So the other guy got 40 seconds, he'll get 10 seconds. That's what you're saying when you say plus 15. You're saying, give me a quarter of what a normal guy would get. What would be the mathematical effect of giving a niceness of minus 20?
Times 2.
What?
Right. It would be 2 times as much. Because it would be 20 minus negative 20. So it would be 40 over 20. Just 2. So it gets 2 times as much.
I think you're right. So let's see. 20 minus 20. So 20 minus 20 is plus 20. So it's 40. So it's 40 divided by 20. Right? 20 minus 0 is 20, because the normal process is 0. So it's going to be 40 divided by 20 is 2, if you're, in most systems of math. So therefore, it would be twice. So basically, the most nice, before you get all excited about giving you, these root giving you a minus 20 niceness, you only get twice as much CPU as everybody else. So you get more, but it's not like you get monopolize it. You just get twice as much. The other guys will still get, and you get twice as much, but you won't get 4 times as much. That's the most you can get. And again, only generally only the super user may set like niceness to a lower value. So you can't just go and give yourself nice. So now, okay, that's the math of nice. Now we can combine the mice of Nath. Somebody's read a book called that, The Mice of Nath. Anyway, nice math, the nice math. Nohup, we talked about that. Means like don't stop it, even if the screen goes away that it was run from the terminal, keep it running. Nohup is often used in combination with nice command to run processes on a lower priority. So, for example, I could do like this. I mean, remember, we actually saw something similar to this in the very beginning of the course. We saw a command called time, and the way time ran was like you ran a program and it timed it for you. So you wrote time, and then the program going to run. So here we're also doing that. We did that here with nice also. We ran nice, where we ran a program with a niceness of this. So here we're doing 2 at once. We're saying, do the following with nohup. What do I want to do? Do a nice. Now I don't give it a number here, but we'll see what it means. A nice of A, and run the program called ABCD and run it in the background. So if you don't specify an increment value for nice, which I didn't do here, the nice command defaults to an increment of 10. So it's as though I wrote minus n10. What's 10? 10 will give me 50% faster, right? No, 50% slower. So this will run ABCD at a priority of 10 more than the default. But it's run in the background. The tilde means in the background. And it's nohup means that, it's going to run no matter, even if I close the terminal. So that's like creating a daemon, if you think about it. I'm creating some process that's going to run in the background forever until it finishes. and I'm giving it a low priority, so I don't want it to, prevent other people from doing their work. That's nice and hup. All right, now I think this is the last topic. This is the last topic and one of the most useful ones for you, actually. At the login, certain files are run, a bunch of files. They usually, a file, oh, first of all, I didn't explain this. I should maybe add this here. I don't know if I explained this. Did I explain hidden files? Most.
Never had called recall.
No. Okay. View present. At login, certain files are run. Most of them are hidden files. What is a hidden file? A hidden file is any file that starts with a dot. When you do ls, it'll show you only the regular files. It won't show you the hidden files. If you want to see the hidden files, you got to do ls -a for all. Then it'll show you files that start with a dot. So in other words, there are these special files that are hidden from view normally. They're hidden from view just for convenience because most people don't want to see them. And those files are usually put there because they're intended that when you log in, they'll be run. You'll run those files automatically. The system just knows to read them and run them. So there's one file called a .bashrc. There's a lot of times it's RC. RC stands for resource. You can have a shell RC or .k shell RC, but you could have a lot of times a .bashrc. And what that means is a resource file, or what we would also call a configuration file, or it's kind of like, it's not a really configuration file, but a resource file, similar to a configuration file that will be run when you log in. You can use this file to run commands, and anything you put there will be run automatically when you log in. So what could you define there? You could define environment variables. You could define your prompt there. You can create aliases, among other things. So we're going to see how to do that. You use the command export so that the variables you define in the bash will be passed to programs that are spawned by the shell and won't just be done to the shell itself. In other words, there's an export command which allows, let's say I make an environment variable like a path. I define my path. Now, the system already defined your path, but let's say it didn't, and you want to define your path, and the system never did it for you. So you would create that path as an environment variable in your .bashrc, and then your shell would know about it. But the problem is, when you ran another program, like your mini shell that you wrote, or any program that you would run, or even a program that already exists, but you're running it now. You didn't write it, but if you run it, it won't get that environment variable unless you do the export command. That's what export does. To run the .bashrc file after you logged in other words, instead of let's say you changed it. It ran when you logged in automatically, but now you want to manually run this bash file. So you can either type source space bash.rc or type dot space bash.rc. It also runs it, but source means basically run it. So you're running the bash HRC. Okay. Now let's see some examples. So first of all, you can make an alias. I can make an alias PD equals PWD. That means anytime I type PD now, it'll be as if I wrote PWD. So I can just save some typing. You could write P if you want. Then anytime you type a P and hit enter, you'll run the pwd command. You could also give it, you could also in the quotes here, you could give it flags. If you want to always run pwd with a certain flag, then you could make an alias for that whole connection. Here I do two things at once. I define my path. This is a bash, regular bash command. Define the variable path, which is the environment variable path, is equal to $path, which is the old path, whatever it was up to now. It's like a equals a plus 1. So path equals path, and then append to it colon tilde bin. So that will include the bin directory in my home directory. In other words, tilde means my home directory. And inside of that, if there's a subdirectory called bin, add that to the path. This is identical to the above, as far as I remember. It's just that I put it in quotes. In other words, here I put in quotes and I put these braces. The point is I wanted to put the braces because how did it know that the variable ended at the H and that this wasn't part of the variable name? I think the main answer is that it knows because this is an illegal variable character. You can't have a semicolon in a variable name. And so since that can't be part of the variable must be ended the one letter before, and therefore it's path. But I can also use the curly braces to say where the end of it is. And I can say, that's what I want you to do there. Because I want you to add the bin to the path. Now I can also do, a lot of times I type grep instead of grep, I type grep. So I can just make grep be an alias for grep. And as long as I put that in my bash RC file, I now have my own special kit. So now you can seem like a really professional Unix user by going into your bash RC and making all kinds of custom-made commands that, you say, oh, I'm doing this stuff, and it look very fancy that you're typing all these custom-made commands that you wrote yourself. So that's a lot of fun. What did I do here? Oh, PS1 is a variable which refers to the prompt. So here I actually define my prompt, and there's special ways that you could define it. I define my prompt to be the word Nachum, followed by the time, and I forget what U is, \U. I'm not sure. It might mean time, but it might, I'm not sure. Oh, it's user. It'll be Nachum. It'll be like this: Nachum space Danzig, because my username happens to be Danzig. The username at host name, linap, or whatever the host name is, /d/t. So that just puts like spaces after it. I don't know why I did that. But the point is I could define my prompt if I know the variable name is PS1. All these things you can look up, and then you can define how your prompt is, or define any other variable. You can get any regular expression, or sorry, any environment variable you're allowed to use and define it here. You can even create a new one. Now here's some stuff that we didn't discuss that we could discuss another time, another year, something like that. Some other commands: top, fstat, lstat, iostat, umask, yes. There's a command called yes, which is a funny command, which just types the number 1 over and over again. Because there are a lot of times that the system comes up and it asks you, do you want to do this? And you just say yes, yes. So if you want to say yes to all, you use this command yes. I think when you type yes, you just get a 1. Somebody want to try that? You have a Unix machine?
For the prompts, when it says either press yes or 1. When it confirm.
What are you doing? You type
Don't you
yes?
have what?
Tried it?
No, I didn't try it. I don't have Unix on me. That's
Oh.
Avraham.
So when you type yes, I think it gives you a 1, or it gives you an infinite list of ones. It starts writing lots of ones to the screen. Because
in
Lots of
my
Ys.
case,
lots of Ys, sorry, lots of Ys. So you use it like sometimes you're installing something and it says, Y/N, yes to continue, no to quit. So instead of sitting there in front of the computer and just typing Y all the time, you just just run the function Y, and you give it this command, and then it'll automatically supply all the yeses.
Do you like pipe the yes program into the
I don't remember exactly how to do it, whether it's with a pipe or whether you just type yes and then the command, or whether you use a redirection. I'm not sure. Try it out.
this program is like the equivalent of a 5-year-old when you ask it a question.
Yeah.
You can keep pressing Y every time.
Yes.
You eventually just give up.
It's a funny thing. There's also one more topic which I didn't explain, which is let's talk about that. P threads. Not going to be on the exam, but unless you want it to be. But I have one more topic that we could talk about. I have got through everything. We can also review. You probably could use that.
Yeah, if you could prepare I guess a relatively condensed review class, I personally would really appreciate, because the other option is just to watch every lecture over again, which is currently my plan.
Well, definitely watch. Yeah, you can watch every lecture again. If that doesn't, you didn't take copious notes?
Yeah, where are your notes, Hess?
I mean, literally my learning strategy is to just keep watching lectures over and over again until I basically have them memorized. Like that's all I did. Well, and I take notes.
That's not a good strategy, by the way. You
Oh, yeah?
should do hands-on. I hope you're doing the homework.
Yep.
Yeah, okay, that's good. Here. There's a couple topics we didn't do. We didn't do semaphores or shared memory, sockets or select. You see, I just want to tell you, in some years, when I first started teaching this course a long time ago, I did one lecture on shell, awk, etc. I didn't do sed. Then I jumped right into fork. That was the next lecture. The next lecture was all the open, close, pipe, dupes, do. The fourth lecture was signal. And that's and basically 4 lectures I did the whole course. And then fifth lecture was semaphores and shared memory, and sixth was sockets and select. And that was it, 6 lectures. Each lecture I did in an hour and a half. And then that would be a condensed version. But then I didn't go into as much detail. I didn't do sed so much. I did a little bit of sed. I didn't give as much detail on bash. I didn't give as much detail on signals. The only thing that's pretty much the same from back then is the fork and the open, close in that whole section. But let's do this P thread. And here, Control A, Control C. That's the wrong thing. Why did I do that? Here. P thread. Too much. Where were we? Saying there's a lot of dead. Are you saying there's a lot of dead time in my class?
What do you say about dead people?
I can't stand dead people. I don't know. I'm prejudiced against dead people. I don't let them into my class. Is that discrimination?
Nah, they're dead.
Not right now. Eventually they'll come back at some point, and then you'll have to probably deal with that.
Once you start picking on the Apache helicopter people, then you'll have problems.
What are those? The zombies that have taken over Apache helicopters?
Now people that identify as Apache helicopters.
It's funny, all of this was taken care. Control Z. That's so good. All this was taken care of by South Park a number of years ago when everyone became dolphins. No, what is going on here? All right, I'm not gonna do this with you. Take too long. All right, never mind. But let's go back over here. I like websites. Websites are great, aren't they? So here's a program. What is a P thread? P thread is POSIX threads. POSIX is like a standard definition of how Unix things should work. And threads, the idea of threads is like fork, like processes. But what is the definition of a thread? Who can tell me the one sentence definition that everybody memorizes?
Process.
What?
Process. A single process.
No, process, a thread is a thread. And there the twain shall meet.
It's the heart of the process. That's what makes it.
No. Oh. No. You're right. You can say a process is composed of many threads. That's sometimes people say. But a process could also be composed, well, a process could spawn many processes. So what's a thread? A thread is like this is the definition that they always taught in the past and that you should remember. A thread is a lightweight process. Now, what does that mean? But that's the words. A thread is a lightweight process. It's a process, but it's lighter. What does it mean, lighter? That's why it's called a thread. It's only a thread. It's not a whole heavy process. It's just a thread.
All the context doesn't get copied over.
Exactly. Not all the context gets copied over. It takes up less. It's easier for the operating system to manage it. It requires less overhead. It's easier. You don't want to make 1,000 processes. The poor operating system will get tired. You can make 1,000 threads. Gives them less work to do. And if you don't need processes, why should you make them? Just make threads. So we prefer to use threads when we can, and usually we can. Okay, so let's look at what we do here. There's a mutex here. We'll talk about that also, but global string. First of all, I make this global string. Why is it global? Why is this global? Because I wrote the word global here?
Because it's before the actual program.
And the global.
Yeah, because it's before, or another way to say it is
Global scope.
It's got a global scope. That's the definition of why does it have a global scope? Because it's not defined inside of any function. It is not local to a function. It's outside of all the functions, so it's global. That is the definition. That is what causes it to be global. Hello world. Now I make a thread function, and this is the key point. What we did before in forks is that we said if you're the child, then do this. Now what we're going to do is we're going to say if you're the child, then do this function. We're not going to have an if. We're going to give it the function we want it to do. So here's the function I want my child to do. I want it to, oh, that's an interesting idea. I should have you guys, or if you, next year or this year, but write your shell using threads instead of forks. But anyway, here, void, I write a function called thread function. And I say int j and int I. And what does I equal? Ooh, that's complicated. I cast it to look, the function got, it's a little confusing. The function got a void pointer. Yeah, I don't know if you're familiar with void pointers. You familiar with void pointers?
It's a pointer that we just don't specify what type it's pointing to.
Yes, yes. Everybody else understands what a void pointer is?
Yes.
It's a pointer where we're gonna have to specify. You can't leave it as a, it basically means that this function can get any kind of pointer. But I'm gonna want it to be an int pointer. So I'm casting it here. Now as I'm expecting it to be an int pointer. So I'm just I'm going ahead and casting it as an int pointer. And then I'm dereferencing it to get the actual int that it's pointing to. And then I'm storing that int in variable I. So I has got whatever I was passed, and j is undefined. Now I say for j equals 0, 1. Well, I didn't define it yet. Now I'm defining it. As long as j is less than int. So if the int I, then so that means if I is like 10, it'll run like, I don't know, 8 times. And j plus, and it's going to do what? It's going to sleep. Now rand modulo 3 means between 1 and 3 seconds, 1 and 0 and 2 seconds, right? Rand modulo 3 will give me 0, 1, or 2. So far the program doesn't do much, just sleeps. Then it says lock this. We can ignore this line for a minute. Let's just say, then it says I equals 10. No, it says if I equals 10, which, notice I don't change I. This is a funny loop. This is a loop that kind of, as long as, oh no, j goes up, right? So I could be 1,000, but if I happens to be 10, remember, I is never changing, but just I'm checking. If I is 10, then write in the global string over here the letter A. Change some letter in the string. I'm just writing to it. Okay. And then I'm changing another letter in the string, AA. So instead of HE, it'll be AA. Else, if it's not greater than 10, then write BB in the thing. Okay, so it's just some kind of very silly program, very silly function. And then what do? I print the string, the global string, and I'm skipping this line. So that's it. Basically, depending on what he gave me, I'm going to put how long is this program going to run? It's going to count up to, it's going to, it's kind of weird because it's hard coded to be 0 and 1. Would have been more interesting if this was, instead of I and j, if this was like j minus 1 or j and j plus 1 or j minus 1 and j. That would have been a little more interesting. That would have put lots of A's in the thing. But let's just say I did only the first 2. Now, so I don't know, whatever it's going to do, it's going to write AA or it's going to write BB. So that's the function I want to do for the child. Now, what does the parent do? The parent comes along and says, first of all, make me a P thread called T1 and another one called T2. I'm using this defined type. I obviously had to include some pthread.h library, POSIX thread.h, right? So I create those. Now we'll skip the mutex for a second, and we'll say create, and here I give it the pointer to the first thread. In other words, first I create the thread. First I sort of create the variable, but it didn't really start running yet. That's just the declaring of a struct or something. Now I give it a pointer to that struct, and I give it null, and I give it the function I want to run, the name of the function. In this case, the name of my function is thread func. So I just gave it that name. And I gave it the parameter that I want to send to the function. You see, how do I give it the parameter for that function? It has to, the function is defined to take a void pointer. I'm giving it an address of a pointer, an address of I, which is essentially the address of this 10 over here. So it's getting the actual 10 and it's checking it over here, and it is 10. So if it's 10, it'll change the first things to A. And then whatever else it does, maybe it goes into a loop, maybe it sleeps, I don't remember. Okay. Now I make J of 13, and I do the exact same line, and I give it J, which is 13, and I run another thread, but here I call it T2. Notice here I create T2. So essentially I created 2 forks or 2 threads, 2 lightweight processes, and they both run, and they both try to write to the first 2 letters of the string, the global string. And then once I do pthread exit null, which actually waits for the thread. In other words, if I just would exit the program, the threads would also exit. By writing pthread exit, I think what it means is that actually it doesn't wait, sorry, but it allows the father to die, but the children to continue running, the threads to continue doing their job. Because notice he just creates them and then goes away. So these will still running. So it detaches the threads. If I did this join here, that would be essentially waiting for the thread to finish. In other words, pthread join on this, join is the opposite of create, kind of. Well, join means like wait until it finished and then, join back up with the thread. So that means wait for it to finish. So what this is going to do in its current form is basically somebody's going to write AA where this HE is, and somebody's going to write BB where this HE is. Who will write first? Who will write second? Who will write last? I don't know. But there's another problem, which is that theoretically, I could have a condition where this is A, and this, in other words, theoretically, I want it to be or AA or BB. But it could happen that these 2 threads that are running in parallel, one will write, he'll write an A, then he'll write a B there. Then he'll write his second B, then he'll come back and write an A. So it could be I'd have AB, hello world, AB low world, or BA. It could be that I don't know, these are running in parallel. I don't know who's going to write first. If I want to lock one, if I want to guarantee that I either have AA or BB, but not a mixture, then I need to use a mutex. I need to lock the variable, and that's what I do here with pthread mutex. In other words, it has a built-in mutex thing to allow me to manage these threads. Now I have to create something of type pthread mutex t, pthread mutex type. I call it mutex, and I give it this initial value, pthread mutex initializer. And then what I do is I only make one of them. So whoever is the first one to do this lock will essentially cause the other guy who tries to do this lock to wait. I will lock him out. Here's what you learned about in operating systems. I will lock him out on that mutex. Now I can change both A or B, whichever one I am. And then I unlock pthread mutex unlock, and I release it. Now I've created an atomic action. Now the writing to that 2 letters of the string is atomic. Nobody else can, well, it's not really atomic, actually. I didn't really make it atomic because I could still get an interrupt there. But even if I got an interrupt, the mutex will prevent anybody else from writing there as long as his code looks like my code. I mean, somebody else could write there, as long as if you didn't use the mutex. But remember, I'm not worried about malicious things. I'm only worried about things that I want, that I'm organizing. So I'll just, before I write, I'll just make sure that it's locked. Make sure that I can lock it, which means that it's unlocked. And so now it'll be either AA or BB, but not a mixture, because I use these mutexes. Mutex is mutual exclusion. That's what it stands for. So you use a lot of times mutex with the P threads to prevent them from like doing things at the same time exactly. All right, here. Okay, any questions on that? No questions?
Yeah, it's straightforward.
Okay. Second example. I don't know. I don't remember what a bad idea was, but let's look at a good idea here. So here, look, let's start at the main. I do like pthread create and pthread create, pthread join, pthread join. So I create them and then I wait for them. Essentially, that's like my wait. I wait for them to finish. So second thread, pthread self is the L. Forget what pthread self gives me. Let's check. Okay, the idea of the, all right, so it just gives the ID. Okay, but what is it, what type of value is it? Says this function always succeeds, returning the calling thread's ID. That's a lot of confidence. Oh yeah, I remember I wrote this thing. It's a very complicated thing I was trying to do here, or it's a very weird thing. I was trying to change, this 42, look, M. I don't want to get into this complicated thing I'm doing here. Anyway, what I just explained is all you need to know. That's how threads work. You create them. You can wait for them with this join, and you can let them work. And as after you created them in parallel, you can also make sure that they don't both get to the same critical section at the same time by using the mutual exclusion function, the mutex. All right, if there's no, there's no questions, we can go back to the, oh, you're saying you want to start a review? Up to you.
Yes.
Yeah, that'd be helpful.
All right, let me stop the recording and do a new recording.